So welcome everyone to TCS Plus. Today's speaker is Tim Roughgarden, and the operator for today's talk is Thomas Hollenstein, and managing other aspects of the organization are those Vidik, Oded Regev, G. Kamat, and Clement Canon. Thomas will now go around the table and introduce the groups.
Thank you, India. So today we have a group from the University of Michigan, represented by Dawei Huang. Hello, Michigan. A group from Université de Paris Diderot. Hello, Paris. We have a group from Caltech by Piyush Srivastava. Unfortunately, we don't have a video. We have a group from the University of Buffalo, Sai Vikrishnar Mani Chayaram. Sorry about messing up your name. And we have a group from New York University, represented by Shravas Rao. Hello, New York. Yes. And we have some more groups which are late and will join later on. So unfortunately for them, they will not be introduced.
So before the talk starts, a couple of reminders. 2 weeks from now, Piotr Wendig will be speaking, and 4 weeks from now, we'll have Virginia Vasilevska-Williams. As usual, during the talk, the groups will be muted, but we encourage you to ask questions, so unmute yourselves and we can have the questions. So today's speaker is Tim Roughgarden from Stanford. Tim has done a vast body of work in algorithmic game theory, approximation algorithms, and things beyond worst-case analysis, and has got a number of awards, including the ACM Grace Hopper Murray Award and the Gödel Prize. In fact, he did a is most known for his influential work in about the inefficiency of Nash Equilibria, which he did during his doctoral thesis, and for which he shared the Gödel Prize. Today, Tim is going to talk about connections between complexity and algorithmic game theory. So, Tim, welcome.
Okay, thanks very much. Hi, everyone. So let me open by thanking the organizers and also the founders of TCS Plus. I think this is a really sort of fantastic initiative to make cutting-edge research open for free to everyone. I've watched several of these seminars in the past, so I'm quite happy to be able to contribute. So the theme of the talk today is connections between complexity theory and algorithmic game theory, meaning the interface between theoretical computer science and economics. Now, some of you may have seen connections in the past between these two fields, and if you have, it was probably about complexity of equilibria. So, for example, how hard is it to compute a Nash equilibria of a bimatrix game? And for a problem like that, where it's phrased as a computational problem, it's no surprise that complexity theory is the right tool to reason about it. And what's different about the things I'm going to talk about today is the motivating questions are actually do not seem computational in nature. They're just more about, say, the existence of equilibria. Yet, despite the fact that it seems to have nothing to do about computation, computation nevertheless governs the answer to these basic economic questions. So that's going to be the theme. Another sort of a subtitle, probably most people think of applied complexity theory as sort of an oxymoron, but that's really kind of exactly what this feels like. It's really using stuff that's from the canon of complexity theory to prove interesting things in a different field. And please feel free to jump in at any time. So my plan for the talk is to give you sort of the highest order bits of a few different papers. Obviously, I won't be able to describe a majority of the results in any of these papers. And so the first one is joint work with Imbal Talcum Cohen on why prices need algorithms. And so here we'll talk about a notion of market clearing of price equilibria with indivisible goods. And we'll show that when you have certain complexity separations between computational problems, that will actually imply the non-existence of these equilibria. Okay, so it's a totally new approach to ruling out equilibria and with some new applications. Then I'll move on to the so-called price of anarchy, which is approximation guarantees for game theoretic equilibria like Nash equilibria. And the goal here is going to be to derive lower bounds on the quality of equilibria, so lower bounds on the price of anarchy, via translation from lower bounds that we already know about, either about polynomial time algorithms or about communication protocols. So we'll translate communication complexity lower bounds into lower bounds on equilibria. The third part of the talk is joint work with Parikshit Gopalan and Noam Nissan. That's going to be about the borders of Bordas Theorem. So Bordas Theorem is a famous and beautiful result from auction theory, which I'll tell you about. But it's sort of, it's sort of very isolated in the sense that it holds only for a special case, namely single item auctions. And we'll show that complexity theory actually explains why no one's been able to generalize significantly Bordas Theorem to much more general settings. And one thing I should say at the outset is that all three of these parts of the talk are totally independent. So if you space out, or if you don't like one of them, just wait a few minutes and we'll restart on a new topic. All right, so let me begin and just sort of jump into the why prices need algorithms. So this is going to be a notion of market clearing, market equilibria. And so maybe in the past you've seen a notion of market equilibria with divisible goods. So when you're thinking about things like milk and wheat. So I'm going to be talking about indivisible items. Okay, so you want to think about things like houses, or a license to broadcast on a certain frequency range in a certain area. So there's going to be a number of items, M items, and then there's people who want these items. Okay, so there's N agents. So we're looking for some notion of supply equaling demand in a market. So it's clear what the supply is, right? We have one copy of each of these M items. So what's the demand? So we have to explain what bidders want. So the model is that each bidder has what's called a valuation. So a valuation is just a set function. It says for any given subset S of items that bidder I might get, what is its value for it, or its maximum willingness to pay, if you like. Okay? And if you're thinking about representation issues, go ahead and think about VI as having some kind of succinct description, polynomial in N and M. Okay, so that's what bidders want. They want high value items. If there are prices, they also want to pay as little as possible. So when we talk about the market clearing, we're talking about an allocation of the items to the agents. So that's just a partition of the item set, okay, into a bundle for each of the agents, S1 through Sn. Okay. All right, so the notion of market clearing is called a Walrasian equilibrium. Okay, and basically this just says we put a price on every item so that simultaneously every bidder is as happy as they could be with respect to these prices, and also the market clears, all the items get taken. So a little more formally, a Walrasian equilibrium, it really consists of two different objects. It's an allocation, so one bundle per player, and it's prices, so one price per item. What does it mean that every bidder is happy? It means, well, amongst all the 2 to the m bundles that bidder I might get, it should be getting the one which maximizes its utility. So its value minus the total sum of the prices for that bundle. Okay, so that should be true simultaneously for each of the n bidders, and the market should clear. Okay, so meaning that all of the items are sold, or if something's sold, the only reason is because nobody wants it, in which case the price is 0. Okay, so that's the definition of a Walrasian equilibrium. An allocation, prices, all the bidders are as happy as possible, and all the items are sold. And so that's the most basic notion of market equilibrium with indivisible goods. So the first thing, whenever you have an equilibrium concept, the first thing you want to understand is existence. So when is this thing guaranteed to exist? So for Walrasian equilibria, sometimes they exist and sometimes they don't. Okay, so it's not as universal as something like Nash equilibria. And so to prove that point and also just make sure you have a sense of this definition, let me go through a small example which has no Walrasian equilibrium. Okay, so to demonstrate this, I only need 2 bidders with 2 items. Okay, items A and B. So the first bidder is an AND bidder. It really wants both of the items. This is also called a single-minded bidder. So let's say the bidder 1 is willing to pay 3 if it gets both of them. Otherwise, it's out. It doesn't want anything unless it gets both. The second bidder is an OR bidder. So it only wants one of the items and it doesn't care which one. This is also a unit demand bidder, it's called. So bidder 2 is happy to have A. It's happy to have B. It doesn't care which. It has value 2, and it has no extra value for a second item. Okay. So I claim that there's no Walrasian equilibrium in this market. Okay, so why is that true? Well, so a Walrasian equilibrium is an allocation in prices. So let's first think about allocations where the AND bidder gets both items. And if you think about it, that's sort of what we want, right? We can't make both bidders happy at the same time. The AND bidder has a higher value, so sort of the socially optimal thing to do is give both items to bidder 1. But the claim is there's no way to price the items that stabilizes that allocation. So why is that? Well, in that allocation, the second bidder gets nothing, right? So for the second bidder to be as happy as possible in getting nothing, it has to be, since it has value 2 from each of the items, it must be that the price of item A is at least 2, and the price of item B is at least 2. If either of those prices was less than 2, then the second bidder would prefer to get that item to getting nothing. So to make the second bidder happy, both the prices better be at least 2. But then, of course, the sum of the prices on both of the items is 4, and that exceeds the value of the AND bidder for these 2 items. So if the prices are that high, we can't make the first bidder happy, giving them both A and B. So that shows that no prices stabilize the allocation where number 1 gets both of the items, and a similar case analysis applies to the other kinds of allocations as well. Okay. So any questions just about the basic definition of a Laurasian equilibrium at this point? Okay, good. So again, feel free to jump in at some point if something's not clear. So this just shows that sometimes you don't have equilibria, but sometimes you do. And really, you know, it's hard to think of a more basic economic question than the existence of equilibria. So it won't surprise you, I hope, to hear that there's a rich literature on exactly this problem. When do you have existence of these equilibria? And I'm not going to give a detailed sort of survey of it, but you know, the most famous result here is a sufficient condition, which is that if all of the valuations satisfy what's called the gross substitutes condition, then you're guaranteed to have existence of one of these equilibria. And so I'm not going to define gross substitutes. We're not going to need it, but basically it's closely related to being a matroid rank function. So it's a subclass of the monotone submodular functions. That's a sufficient condition. It's also a necessary condition for existence under some conditions. So if you have a rich enough family of valuations, and then to this day, there's nice papers coming out figuring out exactly what's the frontier of existence versus non-existence. And in all of these works, when people prove a non-existence result, they do it in exactly the same way we did it on the previous slide. Namely, they just write down some valuations, and they do a case analysis to check that, you know, all possible prices don't work. And that's going to be very different from what we're going to advocate here, which uses a complexity separation, and from it derives an impossibility result without ever actually writing down an explicit example and ever actually doing this case analysis. Okay, so let me state the main result. There's going to be a couple undefined terms, okay, so a couple computational problems which I'll define on the next slide, but I just want to give you a sort of feel for what we're going to do, what's going on, okay? And so this is going to show that under a certain complexity separation, you will not have existence of equilibria, all right? So the theorem's parameterized by a class V of valuations. So this could be, you know, something like all submodular functions. It could be the and or bidders from the example. It could be the different classes studied in the literature mentioned on the last slide, whatever. But just fix some class of valuations V. On the next slide, I'll define 2 optimization problems parameterized by V, welfare maximization and utility maximization. And the theorem says that, you know, suppose it's the case that welfare maximization is strictly harder than utility maximization, in the sense that there's no polynomial Turing reduction from welfare maximization to utility maximization. Then, as a conclusion, we will deduce that there are markets where bidders have valuations in the class V and which do not possess any Walrasian equilibria. Okay. So again, the key point here is that we've connected what would seem to be a purely economic question about the existence of equilibria to just a purely algorithmic one about the complexity of these 2 particular computational problems. That's what's interesting here. So the contrapositive form is also maybe interesting to think about, which is, you know, the only way you have guaranteed existence in a class of markets is if the welfare maximization is at least as easy or as easy as utility maximization. Okay. So that's the theorem, but it's not really a theorem because I haven't told you what these computational problems are. So let me tell you that on this next slide. So again, fix your favorite class of valuations, and again, think of them as being succinctly described. So the utility maximization problem is just the single agent problem. Okay, so that says suppose there's just one agent, they have a valuation, we put prices on the items. What does this bidder want? Okay, so which bundle S maximizes its value minus its prices? So that's the utility maximization problem. The welfare maximization problem is the multi-agent version. Okay, so now you have n agents, each with their own valuation, and now the goal is to find the partition of the item, so the allocation, that makes everybody as happy as possible. Okay, so that maximizes the social welfare, the sum of the bidders' values for the bundles that they get. Okay. Now, because the utility maximization problem has one agent and the welfare maximization has many, pretty much the only 2 cases are either welfare maximization is going to be strictly harder than utility maximization, or they're both going to have the same complexity. And in all cases, the complexity of both are going to vary with how rich the class V of valuations are. Right? So if I make the allowable valuations a bigger and bigger class of set functions, these problems are only going to get harder. Okay, but welfare is going to be, if one of these is harder than the other, it's going to be welfare that's harder than utility maximization. Okay. And so what did the theorem say? Remember the theorem. You have a class of valuations where the only harder problem, welfare maximization, really is strictly harder, does not reduce to utility maximization. That's what triggers non-existence. Okay, then there must be markets which don't have well-rising equilibria. So it's not clear yet. So now the theorem is precisely defined, but it's not clear that it's interesting. I mean, for all we know, right, the hypotheses are never satisfied. So on the next slide, let me give you a couple examples. I mean, one reason I'm doing them is just, to make this kind of abstract formalism very concrete, but also these are going to be two classes of evaluations where the hypothesis of the theorem is met, and therefore we get to conclude the non-existence result for these classes of markets, these classes of valuations. So first, let's just revisit an example where we kind of already know what's going on. So this is the AND bidders, or the single-minded bidders. So suppose now a valuation just specifies, if I'm bidder 1, maybe I really want items 1, 3, and 7, okay, and I'm willing to pay 10 for it. And I'm not willing to pay anything for, a subset of 1, 3, and 7. And again, I don't care about getting extra items. I'm really just focused on 1, 3, and 7. Bidder number 2 maybe wants items, 7, 10, and 12. So suppose valuations are all of this form. Let's look at our two computational problems and observe that it's trivial to understand their computational complexity. So utility maximization, remember this just says you have one agent. So here an agent just wants this one bundle, and I tell you prices, and I want to know what's the bidder's favorite bundle. Well, if you're single-minded, there's only two possible cases for your favorite bundle. Okay? Either, the items that you want, if the sum of their prices is less than your valuation for it, or otherwise the empty set. Okay? You're never going to want anything other than your desired bundle or the empty set, and which is which just depends on the prices. So that's a trivial problem. There's only two cases. You check both, and you can solve this single agent utility maximization problem. Welfare maximization, if you think about it, I mean, suppose everybody's values were just 1 for their bundles. Now you're just looking for the maximum subset of bidders with entirely non-overlapping bundles, aka set packing, okay, or basically independent set. So that's a very hard problem. So certainly assuming P not equal to NP, welfare maximization does not reduce to utility maximization, and that theorem I showed you implies that there will be markets with these single-minded bidders without well-rising equilibria. Now, of course, we knew that. I showed you an example early on, but this was to sort of get us warmed up. I think it's interesting to rederive it through this complexity framework. Here's a different class of evaluations, which, as far as I know, hadn't been addressed previously. Yeah.
So, does that previous result then require the assumption that P does not equal NP in order to show the existence?
So the theorem does not require the assumption that P is not equal to NP.
Right, but to get that result.
Correct. It's a conditional result. Absolutely.
Thanks.
Whereas, so it's in some sense it's weaker than what I showed you on the fourth slide, as Grant's pointing out, because this, here we deduce that you have non-existence, assuming P not equal to NP, whereas on slide 4 I showed you that there are examples without existence, just unconditionally. And in this part of the talk, that will be, if you like, kind of a weakness of the complexity-based approach.
Okay.
So all of our impossibility results will be conditional. Okay.
Thanks.
Yep. Thanks. This is a great question. Other questions? Okay, so a second example, budget additive bidders. So an additive bidder just has some value, Vij for each item j, and then if you give them a collection of items, you just sum up their values for the individual items. So that's an additive valuation. Budget additive just means, okay, in addition, I'll truncate the valuation at a given point. So every bidder has a budget B sub I, and the value is either the sum of the items, or if that exceeds its budget BI, then its value is just BI. It never has value bigger than BI. And again, if you look at the utility maximization and welfare maximization problems, anyone who's taken, undergraduate algorithms and complexity can classify the complexity of both of these problems in about 5 minutes. So basically, because of the budget on the budget evaluations, the single agent utility maximization problem is basically a knapsack problem. So it is weakly NP hard, but you can solve it in pseudo-polynomial time. So it's polynomial time solvable if all of the numbers are small. Welfare maximization with this valuation class is basically bin packing. So basically, to the optimal allocation doesn't want to waste any bidder's budget, and so that's closely related to getting the minimum number of bins necessary to pack a bunch of items. So that's strongly NP hard. So it's NP hard even if the numbers are small. So again, assuming P not equal to NP, welfare maximization does not reduce to utility maximization for these valuations. And so again, assuming P not equal to NP, there exist markets with budget additive bidders for which there are no Walrasian equilibria. All right, so the last thing I want to say about this part, I just want to say a little bit about the proof, because actually the proof is not so difficult. So again, what are we trying to prove? We're trying to prove that the only way that you can have guaranteed existence is if welfare maximization reduces to utility maximization. So let's consider a valuation class, and let's assume Walrasian equilibria are guaranteed to exist. So let me actually sketch the reduction of why welfare maximization reduces to utility maximization. So this is really going to follow from combining two facts. So neither of these facts is trivial, but neither one is especially hard to prove either. So the first fact, I think, it first appears in print in Nissan and Segal. And so they said, well, suppose you make the problem easier. So rather than welfare maximization, I allow fractional welfare maximization. So as a bidder, you might get 10% of this bundle, 40% of this other bundle, and so on. And of course, you constrain that every item is allocated fractionally at most once overall. So the first claim is that if you just want to solve the fractional welfare maximization problem, that does reduce to utility maximization. And basically the way you prove this, so fractional welfare maximization corresponds to a linear programming relaxation of the welfare maximization problem. You pass to the dual of that linear program, and it turns out the separation oracle for the ellipsoid method in the dual is exactly utility maximization. So by at most a polynomial number of invocations of the utility maximization subroutine, you can solve this linear program. So that's the fractional case, and that's not really what we wanted. We wanted to solve the real welfare maximization problem. So the second fact, which was observed in economics back in the 90s, and this is what really kind of connects existence issues to structural properties relevant for algorithms, is that the markets in which a Walrasian equilibrium exists are precisely the markets where this linear programming relaxation is exact. Okay, so where there's an optimal integer solution to the fractional welfare maximization problem. And basically the reason this is true, so remember a Walrasian equilibrium comprises an allocation and prices. So the allocation can be thought of as a feasible integer primal solution. The prices, it turns out, can be thought of as a feasible dual solution. And the Walrasian equilibrium conditions correspond to complementary slackness conditions, which characterize optimality when you have a feasible primal dual pair. So that says that Walrasian equilibria are going to be precisely the optimal integer primal / feasible dual pairs. So if you combine these two together, you get that when you have guaranteed existence, for valuation classes with guaranteed existence, actually even the integral welfare maximization problem reduces to utility maximization problem. And that's what we set out to prove. That was the theorem. So in the paper, there's lots of other stuff. So if this sort of catches your interest, I encourage you to look at it. I kind of gave you the teaser result from the beginning of the paper, but we also give impossibility results for lots of other classes of anonymous and compressed pricing. So any questions before I move on to the second part of the talk?
I mean, just to make sure that I got it. So if in case there's a Walrasian equilibrium in the market, yep, that means both these problems are actually easy, like NP, because the linear programming will solve both these problems.
As easy as utility maximization, right? So
as easy as
right,
which is in pseudo-polynomial time. Is that
for the budget additive case? Yeah. So
okay. Okay.
This is the proof of the totally generic theorem. So, and the impossibility results actually get triggered whenever you have sort of a complexity separation, in the sense that one does not polynomial Turing reduce to the other. So it doesn't actually require that either one be in P per se.
Okay. But the second one is like the separation oracle for the first problem, for the linear programming relaxation.
Exactly.
Okay.
Okay,
great. Thanks.
Yeah. it's guaranteed existence that actually makes you care about the result of the fractional solution, because it'll actually be integral whenever you have guaranteed existence. Thanks for the question. Other questions?
I have a question. Maybe it doesn't make any sense, so if so, just tell me. I'm wondering, I mean, this seems pretty tight. Does it make sense to ask if there is some kind of converse to the theorem?
Good question. Yeah, so in the paper we show that there is no totally general converse. So what would a converse look like? That would say that, you know, whenever you do have a reduction, then you're guaranteed equilibria. Okay, so whenever basically the two problems have the same complexity, that's a sufficient condition, not just a necessary condition, but sufficient condition for guaranteed existence. And in the paper, we do give a quite contrived example where both of these two problems are in P, and yet there are markets with those valuations that do not have equilibria. Now that said, you know, our example is really not very satisfying, and I do think it's a great open question. Is there some kind of you know, restricted converse? So say for classes of valuations that satisfy some kinds of closure properties or something of that nature, maybe you could, you know, prove a converse. That said, it's hard for me to envision exactly what the proof would look like, but that would just make it cooler if anybody proved it. So I think it's a great question. Any other questions? Okay, so let me move on to the second part. Sorry,
Tim, I have a question.
Yeah.
Can you using the two steps, can you morph your proof into a proof that just deals with fractional versus integral points instead of complexity theory things? Like, can you get does it lead you to an unconditional proof?
So what follows from fact 2 is on a market-by-market basis, existence is characterized by the inequality of a certain polytope. So in some sense, you know, that you can think of, you know, but so then it reduces the problem to trying to understand, okay, so, you know, when are you going to have guaranteed inequality of this polytope? But when you rephrase it that way, it becomes much more plausible that complexity has something to say. Although, again, it would only be conditionally. So, I mean, one way to think about this is, you know, so one sort of, you know, very, very kind of generic fact that we're all familiar with is if you have an NP-hard problem, then, you know, and a tractable linear programming relaxation, then unless P not equal to NP, you're going to have instances where the optimal solution is fractional. Right, so that's just true, because otherwise you get a polynomial time algorithm for the NP-hard problem. Now it doesn't actually give you explicit, you know, instance with a big inequality gap. Okay, and so so this is exactly the same thing going on here. So just in the same way that hardness results will often suggest to you the instances which have inequality gaps, but which then needs to be kind of verified directly. Here again, sort of the reductions give you basically candidate markets where you expect there to be no horizon equilibria, but then you really do have to actually directly check that it's not there. So it certainly gives you a recipe for how you would make these unconditional.
Yeah, so like in the second example you showed with the truncated prices, can you get an unconditional bound here by using an inequality gap argument?
Right. So presumably, I'm embarrassed to admit we haven't actually done that, okay. But I don't expect it to be difficult.
Yeah.
I mean, famous last words, but that's my guess. Yeah. So, and one thing that's interesting. So in this next part of the talk, there'll be sort of a similar moral where we get lower bounds without explicit constructions. But in contrast to the first part, I mean, in this part, I really think we're going to get results that it's hard to imagine how you would ever prove them from an explicit construction. So in some sense, the payoff's going to be, you know, in the first part, I think, you know, it's what's nice about it is, first of all, it's just maybe conceptually surprising. The complexity is useful for addressing these questions. Second of all, you know, for someone who knows undergraduate algorithms and complexity, it gives you a very kind of easy and systematic way to understand when you have equilibrium and when you don't. But, you know, at the end of the day, probably many of the things that you will prove, you could have perhaps with more work proved directly. In this part, and I'll make this clear, you know, some of the payoffs here will be things that are kind of unimaginable through explicit constructions. Okay, so the goal of this work is to understand, are there senses in which game theoretic equilibria, like Nash equilibria, are computationally more powerful than polynomial time algorithms? And so that's sort of a vague question, but there are senses in which we already think that the answer to this question is yes. So I mentioned this at the very beginning of the talk, but some of the greatest hits of algorithmic game theory show things like we don't expect that there's a polynomial time algorithm for, say, computing a Nash equilibrium of a bimatrix game. It's what's called the PPAD complete problem. So that's a sense in which equilibria cannot just be simulated by polynomial time algorithms, opening up the possibility that equilibria can, in some sense, compute things that are not within reach of efficient algorithms. And so that means on the lower bound side, it's non-obvious what are the limits on what equilibria can do. What can they compute? What can they optimize? And so here again, the paper has sort of many versions of this meta theorem. I'll just sort of give you one example to illustrate the point. And the meta theorem says that equilibria, even when they're not computable in polynomial time, they're nonetheless bound by the same kinds of limitations that we've proven for algorithms with polynomial computation or communication. And the basic reason for this is that while not always polynomial time computable, they still have sort of low enough complexity that it triggers the typical kinds of intractability results that we prove. And the two main things that we're going to need, so this is true very generally, as long as the equilibrium notion you're talking about is guaranteed to exist. So you might want to think about mixed Nash equilibria, say, which always exist in finite games. And secondly, we're not going to assume that you can compute one efficiently, but if I hand you an alleged equilibrium on a silver platter, you should at least be able to verify that it's an equilibrium in polynomial time or efficiently. Okay, so that's really the two properties of equilibria that are going to drive these lower bounds: guaranteed existence and efficient verification. Okay, so you can apply these results to many different application domains. I want to keep it simple for the talk, and also sort of keep it, to keep continuity with the first part of the talk. So I'm just going to show you one application, which again is to this welfare maximization problem. So it's the same setup as with Horizon equilibria. You have m items, you have n bidders. Bidders have valuations, and you ideally would like to maximize the social welfare. You'd like to allocate the items to make the sum of the valuations as high as possible. Now, in the first part of the talk, I was thinking about computational complexity, so I encouraged you to think about succinct valuations. You can do that same thing here, but for variety, let me work in a communication model. So it's going to be a number in hand type multi-party model. So the parties just correspond to the bidders, and the private input of an agent is just its set function. It's just its valuation. Okay, so each bidder has a private input of length, basically 2 to the m. And we're going to be interested in solutions, or at least the communication problem is it's about protocols which use a reasonable amount of communication, meaning polynomial or at the very least sub-exponential in m. Okay, so the basic communication problem says for some class of valuations, so submodular valuations or whatever you like, to what extent can you approximate the social welfare using communication protocols with modest communication, sub-exponential in m. So as we'll see, so this problem is pretty well understood for the last 10 years or so, the communication complexity of welfare maximization. That's not really what I'm interested in here. That'll be a tool I use. But ultimately, what I really want is I want lower bounds on the so-called price of anarchy, on how good equilibria can be in simple auction formats. Okay, so that's my motivating question. When do simple mechanisms, when do simple auctions work well? And we're going to show that communication complexity allows us to answer this question. So on this slide, I'm not going to define what I mean by simple. I'll define that on the next slide, but I'll give you a concrete example of what I mean by a simple mechanism, and then I'll also explain what I mean by work well. So here's one example of a simple mechanism that I want to think about. Okay, simultaneous first price auctions. So the idea here is, suppose you're a seller and you really have these 20 items that you want to sell. How should you do it? Well, the first thing you might try is to just, in effect, basically slap all the items up on eBay. So just sell each item independently using a single item auction. Okay, so I'm gonna talk about first price auctions, but it really doesn't matter. If you prefer second price auctions, that's fine too. Okay, so the claim is this is a game. So if you have bidders with valuations and you sell all the items in separate auctions, we can think of it as a game, and we can talk about its Nash equilibria. Right? So the players are just the bidders. What's the strategy set of a player? Well, it's just to submit one bid on each of the items, And I want you to notice, in what sense is this simple? The private input of a bidder is 2 to the m parameters, right? Its valuation is a set function, so it has length 2 to the m. But the bidder is only, in some sense, expressing m numbers. It's only submitting one bid on each of the m items. So in that sense, it's a simple mechanism. What's the payoff of a bidder? Well, you just look at the value of the items that it wins. Okay, so you look at the items on which it's the highest bidder. You look at its value for that collection of items that it wins, and you subtract off the payment it has to make, which in a first price auction would just be the sum of its bids on those items. Okay, so those are the players, those are the strategies, and those are the payoffs. So we've defined a game, and we can talk about its equilibria. So by a simple mechanism working well, what I mean is that all of its equilibria, say mixed Nash equilibria, should be near optimal, meaning the expected welfare of any equilibrium should be almost as high as the holy grail of the allocation of items that maximizes the sum of everybody's valuations. Okay, so that's the price of anarchy. It's exactly this ratio between the optimal welfare and that of the worst equilibrium. So the closer this ratio is to 1, sort of the better the mechanism is doing at optimizing the social welfare. Okay. And so the goal, and again, the theorem is going to be about how do we prove lower bounds on the price of anarchy of simple mechanisms. Okay. So here's what the main theorem is going to be, and there's a lot of text on this slide, so let me actually sort of break it into 2 pieces. So first, let me tell you that there's going to be some hardness assumption, and I'll tell you what that is in a second. But let's look at, what do you get if the hardness assumption actually holds? So what you get is lower bounds on the price of anarchy, on how good equilibria can be. Okay, and it's going to be a lower bound, and this is important, that applies not just to a single mechanism like simultaneous first price auctions, but this lower bound will apply to every possible simple mechanism. Okay, so now let me tell you what I mean by a simple mechanism. I mean it's one in which every player has the number of actions available to a player is sub-doubly exponential in the number of items m. So to help you interpret this, let's go back to last slide, simultaneous first price auctions. How many actions do I have in a simultaneous first price auction? Well, there's m numbers I'm submitting. Okay, so imagine we discretize, so I have some constant number of options per item. Then that's a singly exponential in m number of actions in a simultaneous first price auction. In an auction where I asked a bidder to bid on every possible bundle it might get, that's 2 to the m bids, so that would have a doubly exponential number of actions. So that I'm not calling simple. But anything with a sub-doubly exponential number of actions, certainly including simultaneous first price auctions or any other sort of simultaneous single item auction format, that's what's going to be called simple, and those are the mechanisms to which this lower bound will apply. And the lower bound is going to say that the price of anarchy is at least alpha with respect to any simple mechanism. Okay. All right. And so, one technical fine print is actually the lower bound is not for exact mixed Nash equilibria. It's for approximate Nash equilibria. So that's a weaker lower bound because there's only more approximate Nash equilibria. In my defense, epsilon can be really, really small if you want. It can be even sub-exponential in n and m. I don't actually know if the theorem is true with epsilon equals 0. That's an open question. Okay, but certainly for very close to exact mixed Nash equilibria, you get the lower bound. So what is the hardness result which gives you this conclusion? It's an assumption about the non-deterministic communication complexity of the underlying welfare maximization problem. Okay, so the hardness assumption says suppose there is no efficient protocol, sub-exponential communication protocol, that distinguishes better than an alpha factor between high welfare and low welfare solutions. Again, it should be a lower bound also for non-deterministic. So basically, not only can you not compute an alpha approximation, but you also can't even certify that the welfare is at most some number better than a factor of alpha. And we'll see where the non-determinism comes in the proof. Okay, but so that's the formal statement. If there's a lower bound for non-deterministic approximation of social welfare, that exact same lower bound carries over to any simple mechanism for bidders with those valuations. All right, so again, we have this theorem, and it's not, without examples, it's hard to know what to make of it, right? So, what do we, when is this hypothesis satisfied in any interesting cases? And here the answer is, a resounding yes. So last decade, people really nailed down to a good degree what kind of approximation of social welfare you could get in various settings. And so let me just, again, there's results for many other evaluation classes as well, but let me just instantiate one of them. So let's think about subadditive valuations. Okay, so what does that mean? Well, that means if you give a bidder the union of the bundles A and B, then its value is at most its value for A plus the value for B. Okay, so that's a subadditive function. This is still more general than, say, submodular functions. So Dobzhinsky, Nissan, and Shapira proved, and this is it's a quite direct reduction from multi-party disjointness, that when bidders have subadditive valuations, you cannot approximate the social welfare better than a factor of 2 with any sub-exponential protocol. Okay? And it wasn't really important for them, but the proof being from disjointness is also for the non-deterministic communication complexity. So now we can just invoke the theorem I told you about on the previous slide. So now if you look at any simple mechanism, so certainly simultaneous first price auctions, which have only an exponential number of actions, but any mechanism that has a sub-doubly exponential number of actions per player is going to have price of anarchy at least 2 for bidders with subadditive bidder valuations. Okay, so there will be Nash equilibria which are off by a factor of 2 from optimal. Okay? And this is now unconditional because we're deriving it from communication complexity. So this connects to a couple other recent results in interesting ways. So last year, there's a very nice paper by Christodoulou, Kovacs, Skorica, and Tan. So what they did is they focused on the specific case of simultaneous first price auctions. And for the case of subadditive bidder valuations, they really exhibited an explicit construction. And this is unlike the Horizon Equilibria. When you're talking about games with many players and sort of complicated payoffs like simultaneous first price auctions, this is actually really hard. So this is a tour de force result. They wrote down valuation profiles, they solved for a Nash equilibrium with respect to them, and showed that the welfare of this equilibrium really is off by a factor of 2. Okay. So on the other hand, this new theorem, it sort of regenerates this lower bound, modulo this epsilon around the equilibria, just by standing on the shoulders, just by piggybacking on our sort of very mature understanding of non-deterministic communication complexity. Okay, so as a simple mechanism, this factor of 2 from communication complexity certainly applies to simultaneous first price auctions. But I think, so more importantly is that, the statement that any simple mechanism suffers a factor 2 loss, I can't imagine how you would prove that through explicit constructions. Because if you've ever actually, had to solve for equilibria in some non-trivial games, one thing you learn is that the equilibria can sort of dance all over the place as you vary the payoffs in small ways. So it's very discontinuous, the Nash equilibria, in terms of the format. So you'd really, I would think you'd have to redo the explicit construction for every new simple auction format that you considered. So even just going from, say, first price auctions to second price auctions, you have to redo the example. So I'm not sure how you'd ever get the sort of sweeping lower bound if you were really, had to auction by auction come up with bad equilibria. Another interesting aspect, so there's a great result by Feldman, Fu, Gravin, and Lussier. This was in stock 13. And so they were working on the upper bound side. So what they proved is that for simultaneous first price auctions, when bidders have subadditive valuations, every equilibrium is in fact within a factor 2 of the maximum possible, which is kind of amazing because it's a pretty hard optimization problem, and yet equilibria, already do get a 2 approximation of it in simultaneous first price auctions. So that, of course, nails down the right answer for simultaneous first price auctions. The price of anarchy is exactly 2. But the fact that we have a lower bound for all simple mechanisms and then a matching upper bound for this specific format of simultaneous first price auctions, this is a sense in which simultaneous first price auctions are actually an optimal simple mechanism. Okay, so in the sense that it has the minimum possible price of anarchy of any mechanism with less than a doubly exponential number of actions. Okay, and so, and again, I'm not sure how you could make these kinds of optimality statements without going through the kind of complexity-based lower bounds that I'm describing here. So that's an example of how you apply this. So just briefly, where does the epsilon come from? Why approximate Nash equilibria? This is also relevant for the proof. Well, at the beginning of this part of the talk, I said that what really drives the lower bounds are guaranteed existence of equilibria and efficient verifiability. Okay, so meaning if I hand you an alleged equilibrium, you can verify it in polynomial time. And with exact Nash equilibria, verifiability is an issue. Okay, so even just think about a simultaneous first price auction. So we agreed that the number of actions available to a player in a simultaneous first price auction is exponential in the number of items m, because you have m different decisions to make. Now, what does a mixed Nash equilibrium look like? Well, it's a probability distribution for each of the players over its available actions. So if a player has an exponential number of actions, even just writing down one mixed strategy requires an exponential number of parameters. Okay? So forget about verifying the equilibrium. I can't even write it down in a polynomial description. So the way we get around this is by leveraging a quite well-known theorem of Lipton, Markakis, and Mehta, which says that if you pass to epsilon approximate Nash equilibria, where every player is using strategies within epsilon of their best response, then in fact there's guaranteed to exist Nash equilibria with very small supports. So logarithmic in the overall number of actions. And so that means that, so for example, in a simultaneous first price auction, there will be epsilon Nash equilibria that have polynomial description length. And if you have a sub-doubly exponential number of actions, you'll have sub-exponential description length. And so the idea of the LMM theorem is you just it's a sampling argument. You start from a Nash equilibrium, you take a bunch of independent samples from it, you apply Chernoff bounds, you observe that you get an approximate Nash equilibrium, and that's how it goes. All right, so that's where the epsilon comes from. Let me actually sketch the proof of this theorem, and you'll see, really how the guaranteed existence and how the efficient verifiability makes it work. Okay, so let's assume that no non-deterministic communication protocol gets a better than alpha approximation. Let's prove that the price of anarchy of any simple mechanism also cannot be better than alpha. So for contradiction, let's assume that actually the price of anarchy was small. All right, so alpha is the assumed hardness for the communication problem. Rho we're going to assume is the price of anarchy. And suppose it was actually less than alpha. Let me show you how we could get a non-deterministic communication protocol to solve the social welfare problem better than alpha. Okay. So as input, think of it as a promise problem. So I give you, there's going to be valuations. So it's again sort of a multi-party number in hand setup, and I promise you that either in case 1 there's an allocation with total welfare at least W star, or in case 2 every allocation is worse than W star over alpha. Okay, and so when we're talking about the non-deterministic lower bounds, clearly I mean for part 2. Right? It's easy to certify you're in part 1. You just exhibit an allocation with high welfare. It's not clear how I would certify that we're in case 2, that no allocation could be good. Okay, so I need to assume something about the non-deterministic communication complexity. So how do I use that? Where does the non-determinism come in? Right. So a non-deterministic protocol, one way to think about it is some centralized authority writes something up on a shared blackboard, and then all the players independently accept or reject. So what is this centralized party going to write on the blackboard? Well, it's going to look at all of the valuations and compute a small support approximate Nash equilibrium. And such a thing exists by the LMM theorem. All right, so this is exactly what the prover uses as its proof. Okay, it writes down an approximate Nash equilibrium, an alleged approximate Nash equilibrium. Okay. Now, what do the players do when confronted with this, potential approximate Nash equilibrium? Well, the first key point is that the players can verify that it's an equilibrium with no communication at all. Right? So if the prover writes on the blackboard, what strategies I'm proving, and it writes on the blackboard the strategies being followed by all the other players, the mixed strategies, I can just check myself, am I in fact only playing epsilon best responses with respect to what other players are doing? Okay, so if all of the players accept their own equilibrium conditions, this verifies that it is indeed an approximate Nash equilibrium. Once it passes that test, now you look at the expected welfare of this approximate Nash equilibrium. And again, this is something every player can contribute their own contribution to the welfare privately, and then it's straightforward to just sum them up and check the total welfare. So now what happens, if the welfare is high, meaning higher than W star over alpha, then of course we have to be in case 1. Okay, but this is not the interesting case. It's easy to certify that the welfare is high, and so we're not really using anything in part 1. This is the interesting part of the proof. Okay, so the interesting part of the proof is that the approximate Nash equilibrium can act as a short and efficiently and a privately verifiable certificate of low welfare. Why? Well, suppose all of the players compute the expected social welfare of this equilibrium, and they discover that the expected social welfare is at most W star over alpha. Okay, that's the second case. Now, by virtue of the price of anarchy being small, okay, by assumption the price of anarchy is at most rho, what does that mean? That means the optimal solution can only be a rho factor larger than any equilibrium. here's one equilibrium. The optimum can only be a rho factor larger. So the optimum's at most rho over alpha times W star. And if rho is less than alpha, this is a checkable certificate that we're in case 2. Okay, that we actually were in the low welfare scenario. So this shows that, given a too good to be true price of anarchy bound, rho better than alpha, you get a too good to be true non-deterministic protocol for certifying either side of this hard welfare maximization problem. So any questions about that? Okay. So again, the paper has many more applications, both to combinatorial auctions and to other domains like routing games. I'm going to skip this so I can at least say a little bit about the borders of Bordas Theorem in my remaining time. Okay, and so like I said, this is going to be joint work with Parikshit Gopalan and Noam Nissan. So basically what Bordas Theorem is about is it gives a really nice description of a projection of a certain polytope. Okay? This polytope is meant to be the design space for single item auctions. Right? So bear with me for a few slides while I develop the terminology I need to state Bordas Theorem, and then I'll be able to say why complexity is a barrier to generalizing Bordas Theorem beyond single item auctions. So in this final part of the talk, it's going to be in some ways simpler than the first 2 parts. No longer do we have many items. Now we have just one item. Okay, so it's a single item auction. And so now, a bidder is much simpler than before. No longer do we have some set function VI. The only unknown data is how much bidder I would be willing to pay for the item. That's its valuation V sub I. Now, Bordas Theorem is totally bread and butter traditional economic auction theory. And in traditional auction theory, what they do is average case, or also known as Bayesian analysis. So there's going to be a positive distribution over the inputs. So the input here is what each bidder would be willing to pay for the item. We're going to assume that VI is drawn from some distribution FI. We're going to assume that the seller or the auctioneer knows the distributions F1 through Fn and is only unclear on the actual realization of V1 through Vn from F1 through Fn. Okay, so that's the setup. So bidders have private valuations drawn from known distributions. A natural question is, okay, I want to sell this one item. How should I sell it so that my expected revenue is as large as possible? And here the expectation is over the assumed input distribution. Okay. So, what might a single item auction look like? Well, we already talked at one point about the second price auction. So that's where the highest bidder wins and pays as a price the second highest bid. So in a second price auction, it's a dominant strategy to bid your true valuation. A little twist you can do is you can add a reserve price. So that would correspond to an opening bid in eBay. And so then the winner is the highest bidder who clears the reserve, if there is any such bidder. And then if there is a winner, what they pay is the larger of the reserve price or the second highest bid. And again, that's exactly how, for example, eBay works. All right. So we have the space of single item auctions. We have an assumed distribution over inputs. And the question is, which auction is best for the seller in the sense that it generates the largest possible expected revenue? So this question, solving for the optimal auction as a function of the distribution, it was completely nailed in a beautiful paper by Meyerson back in '81. So he really gave, more or less a closed form formula for saying, you tell me the distributions F1 through Fn, I'll tell you exactly how you should sell your item. And it's going to maximize expected revenue over anything you could possibly do. In general, this optimal auction can be pretty complicated, but sometimes it's really nice. So for example, if all of the distributions are the same, you actually get the kind of amazing punchline that eBay is optimal. A second price auction with a suitable reserve price is actually the best thing you can do in symmetric situations. So this is a landmark result, Meyerson's result, and so people wanted to generalize it in all kinds of ways. So for example, Maskin and Riley, this is later in the 80s, again two extremely well-known economists, so they asked, well, they wanted to solve harder auction problems. The details aren't important for us. They were motivated by risk-averse bidders, but they said, can we have some systematic way for solving for optimal auctions? So Meyerson's analysis is basically purely analytical. He basically just kind of directly used calculus, in effect, to solve for the optimal auction. In the more general Maskin and Riley framework, and this is what led to Bordas Theorem, they, again, as economists, at the end of the day, they wanted sort of closed form solutions, but their proof methodology would look to us really like optimization, like mathematical programming. Okay, so let's say linear programming. And that's a very natural thing. So you're asking, you know, I want the optimal single item auction. Can I write this down as, for example, just maximizing some linear objective function over some polytope? And if so, presumably that gives you both structural and computational properties that you want. All right. Okay. So what I want to do next is make this a little more concrete. Okay. So again, at a high level, we have the space of all single item auctions, whatever that might look like, and we want to maximize expected revenue over them. And the question is, can we usefully encode that as a linear programming formulation? So what I want to do on the next slide is I want to show you that if we resort to a very large number of dimensions, then certainly we can encode this optimal auction problem as a linear program. Now, to be computationally useful, one would need to somehow project to a smaller number of dimensions. And there's a question of whether or not you can do that, and Bordas Theorem will be the solution. So it's going to take the high-dimensional linear program on the next slide and turn it into a low-dimensional linear program on the slide after that. Okay. So let me show you how you can encode the space of all single item auctions as a linear program. So what are the decision variables? Okay, well, as a single item auction, fundamentally, what do you have to decide? You have to decide, first of all, you're given input, you're given a bid for each of the bidders, and as a function of the input, you have to decide who wins, if anybody, and what does the winner pay. So we're just going to have decision variables that encode that directly. Okay, so xi of b is just the indicator variable for whether or not bidder I wins when the input to the auction is the vector b. Okay, in a randomized auction, it could be a probability if you want. All right, so x says who wins, p just says who pays what. Okay, so p is just the payment made by bidder I when the collection of bids is boldface b. So a second price auction, for example, all the xi's would be 0 except for the highest bidder where it would be 1. The payment would be 0 everywhere except for the highest bidder where the payment would be equal to the highest bid by somebody else, the second highest bid overall. And more generally, you know, any auction, you know, what it's doing can be encoded in this way. Now, there need to be constraints, however. And there's two types of constraints. So the first two constraints are a concession to the fact that the bidders are strategic and they can do whatever they want. So somehow, if you're analyzing, you know, if you're making assumptions about the outcome of the auction, it should be the case that those really are the outcomes that would happen with strategic bidders, i.e., it should be that those outcomes really are the equilibria. So, you know, usually for simplicity, you focus on the case where truthful bidding is an equilibrium, like in second price auctions. Turns out that's without loss of generality. Something called the revelation principle, which is really just sort of a simulation argument, says that, you know, general auction design reduces to truthful auction design. So don't worry about the truthful constraint. That shouldn't bother you. And so then what you want to say is, you know, for each bidder, it should be in their best interest to bid truthfully. Okay? And, you know, I'm not going to do it here, but it's straightforward to express that as a linear inequality in the x's and the p's. Right? You just want to say, you know, the value times the winning probability minus the expected payment is at least as high when you bid truthfully as when you bid anything else. Okay, so it's straightforward to make that a linear inequality. And then the other thing which is important, of course, is feasibility, which says that there, you know, you only have one item to sell, so there should only be one winner. So the sum of the xi's should be at most 1, no matter what the input b is. Okay. And then again, if you wanted to sort of maximize revenue, that would be simply expressed as a linear function in the p's in the objective function. So again, the details here aren't so important. I mean, what I want you to find it plausible, you know, that if you're willing to use this set of decision variables, then yes, certainly you can phrase optimal auction design as a linear program. So I want you to find that plausible, and then I also want you to observe that the issue with this linear program is that there's an awful lot of decision variables, right? So even, for example, if every bidder is only going to bid either 0 or 1, that would be 2 to the n different possible inputs, 2 to the n possible bid vectors b. Okay, so the number of decision variables in this linear program is exponential in n, which is problematic, certainly computationally, but even as far as the structural insight you get is not so good from this linear program. Okay, so that's the naive one, the high-dimensional one. Now I need to tell you about the projection, and then Bordas Theorem will just be a statement characterizing this projection. So what's the idea behind the projection? So we want to use a much smaller set of variables, a set of variables which is growing linearly with the number of bidders n rather than exponentially. So what's the idea? Well, the idea is, you know, think about it from a bidder's perspective. Okay, as a bidder, what do you really care about? You're trying to say, you know, should I bid 10? Should I bid 12? What should I do? So what information do you need to make this decision about whether to bid 10 or whether to bid 12? Well, if you're risk neutral, which is what I'm going to assume here, all you really care about is, you know, how frequently will I win when I bid 10? How frequently will I win when I bid 12? What do I expect to pay when I bid 10? What do I expect to pay when I bid 12? If you tell me answers to both of those questions, I know, because I know my own value too for winning, I can decide whether to bid 10 or 12. Right? So all I care is about the frequency with which I win at a given bid and what I expect to pay. Now, just remember, so when I say, you know, if I bid 10, what fraction of the time do I win? Remember, we're in this average case analysis world. So other bidders have random valuations. In some cases, you'll win with a bid of 10. In some cases, you'll lose. Okay, so the probability and the expectation is always over everybody else, okay, and what their valuation wound up being. So the idea is to have this new linear program where these only quantities that matter are the decision variables. So Y now just says what fraction of the time will I win when it bids BI. Q is now just the expected payment. Okay? And I want you to observe that these are now a function only of bidder I's bid and not of the full n vector of everybody's bids. So that's why the number of decision variables is now just scaling linearly with the number of bidders, not exponentially with the number of bidders. Similarly, if you think about it from the seller's perspective, if the seller's risk neutral, all they care about is the expected payment they're going to get from each of the bidders. So the objective function can also be written as a linear function of the Qs. So we've argued that, you know, what bidders care about can be modeled using this small set of decision variables. What the seller cares about can be modeled, but there's still an issue. Okay, there was actually one thing that it was important to keep track of, input by input, not just on average, and that was the feasibility constraints. Okay, we're not okay with selling the item at most once on average. Okay, we only have one item all the time, so all the time we need to sell only one item. Okay, so this is the one constraint on the previous slide where it's unclear how to rephrase it in terms of the Ys. Okay, really is fundamentally keeping track, input by input, that the outcome is feasible. So the question that Bordas Theorem addresses is, you know, can you rewrite this feasibility constraint purely in terms of the Ys, thereby getting a low-dimensional linear program, okay, and thereby getting, you know, much better computational results and much better structural results. Okay. So that's the question. So given, basically the question is to understand the interim feasibility question. So if I give you a vector of Ys and I claim, you know, that these are interim feasible in the sense that there really is some single item auction, there's some Xi's, so that these Y's are the corresponding marginals, or am I lying? Or is there no X that projects down to Y? And again, I mean, if this seems a little abstract right now, I mean, really, probably many of you have faced sort of a similar issue in many different situations. So, you know, so this question of like consistency of marginals, you know, comes up all the time in, you know, hierarchies of LP and SDP relaxations, for example. I mean, just to make it very concrete, imagine that, you know, there's some domain of 3 tuples, and I claim that there's a certain marginal distribution of the first 2 components, there's a certain marginal distribution of the second 2 components, and a certain marginal distribution over the first and the third components. The question here is there or is there not some joint distribution over 3 tuples so that all 3 of those alleged marginals are respected or not? Okay? So that's the kind of question we're asking. Given the Ys, are they induced? Do they arise as the marginals from some set of X's or not? Okay, so I'm about ready to state Bordas Theorem, which characterizes exactly which Ys are interim feasible and which ones are not. So to state it, let me first tell you, okay, suppose I wanted to convince you that some set of Ys was not interim feasible, that there was no possible single item auction that could ever have these interim winning probabilities. How would I do it? So here's a certificate. Okay, so here's a way to prove to you that the Ys have to be infeasible. So what we're going to do is we're going to pick for each bidder a subset of its possible valuations, and we're going to call them special. And I do this in some arbitrary way. So, you know, bidder 1, maybe it gets to be special if its value is 1, 3, or 7. Bidder 2 gets to be special if its value is 4, 10, or 12, and so on. Okay, so I just designate a subset of the possible valuations as special. Let me now state to you a linear inequality. Okay, and so one side will be sort of linear in the y's, the other side will be a constant. So the first quantity I want to think about is, let's look, okay, so imagine there was some single item auction, you pick your favorite one, and imagine we just, sampled at random valuations for the bidders, and we see who wins, if anybody, okay, in some single item auction. And we say, what fraction of the time is there a special winning bidder? Okay, so what fraction of the time does bidder win while having valuation 1, 3, or 7? Or bidder 2 wins when its valuation is 4, 20, or 12, or so on? Okay, so what fraction of the time is the winner of this auction special? So this is actually just a sum of these y variables. So remember, what is y? Y says what's the fraction of the time that a bidder wins when it bids or has some valuation b sub i. So this probability here is just the sum of these interim feasibility probabilities summed over the special valuations of all of the bidders. Okay, so it's just a linear function of the y's. Let's think about a different quantity, which says, forget about the auction, put the auction aside. Let's just sort of draw valuations for bidders, and let's look at what fraction of the time at least one of the bidders winds up being special. Okay, so either bidder 1 is 1, 3, or 7, or bidder 2 is 4, 10, or 12, or whatever. And we don't even look at who wins. Okay? Certainly, no matter what the auction is, the probability that there's a winning bidder who is special is bounded above by the probability that some bidder is special, winner or not. Right? It's just a subset of the event. So, if this inequality were flipped, if in fact the sum of the alleged winning probabilities in the y's exceeded this constant, the probability that some bidder is special, then there is no way that the yi's are interim feasible. They have to be infeasible. Okay? So again, summarizing, this is a certificate of infeasibility. If I can ever find a way of designating valuations as special so that the alleged sum of winning probabilities of special valuations exceeds the probability, according to the prior, of existence of a special bidder, it's definitely out. Forget about those y's, infeasible. So Bordas Theorem now states exactly what you hope would be true, which is that this is a complete set of certificates of infeasibility. So if none of these certificates work, then actually the alleged interim feasible rule really is interim feasible. Okay? So a collection of marginals, these yi's, they're induced by xi's, if and only if, for all ways that you might designate subsets of valuations as special, the winning probability of a special bidder is at most that of the existence of a special bidder. Okay, so Bordas' original theorem used some somewhat heavy machinery. Now, actually, we understand that you can derive Bordas' theorem from max flow min cut. So it's actually a quite cool proof of it at this point, which I don't have time to talk about. Okay, so that's Bordas' theorem. Okay, so again, summarizing, we had this what did we want to do? We wanted to solve for the optimal single item auction through linear programming. Our first cut attempt used a huge number of dimensions, but you can project down to a polynomial number of dimensions. The part which is tricky is the feasibility constraints, but basically Bordas' theorem tells you exactly how to plug in a big set of inequalities in terms of just the y variables, which is exactly simulating the feasibility constraint in the original high-dimensional space. So put differently, it's a sort of explicit description of the projected polytope. Okay, so Bordas' theorem. This is a fantastic theorem. It's just very, very elegant. If you wanted to criticize it, you'd say, well, it was really only about single item auctions, right? And we'd like to do more. For example, I mentioned Meyerson's theory about solving for the optimal auction. His theory is much more general than single item auctions. It handles lots of other settings as well. So why can't we have a version of Bordas' theorem which is as general as Meyerson's theory? And this is something people have thought about. Bordas is a well-known and important result, so people have thought about extending it. There are some mild extensions. So for example, if you have not one item, but you have a bunch of copies of the same item, and every bidder only wants one copy, then you can extend Bordas' theorem and again characterize the relevant projected polytope. Also, if you're willing to lose a 1 plus epsilon, if you're willing to go to sort of p-task type results, then there's some quite general approximate versions, especially by Kai Daskalakis and Weinberg. But if you really wanted the full elegance of Bordas' theorem, an exact characterization of the auction design space in terms of these interim rules, it was open whether Bordas' theorem could be significantly extended. And so what our work shows is that, in effect, unless the polynomial hierarchy collapses, then there are no extensions of Bordas theorem significantly beyond single item auctions. So I'm running low on time, so let me just maybe tell you one high order bit of the. Let me at least sort of tell you what the formal statement is, and then I'll skip to the end. And if there's questions, I can talk more about this afterwards. So I do feel like I owe you a formal statement, though. So what does it mean to say Bordas theorem cannot be extended? Right. So to say that analogs of Bordas theorem do not exist, I need to give you a precise definition of a Bordas-like theorem. And so maybe your first thought would just be, oh, well, a linear description of the projected polytope. Maybe that's a Bordas type theorem. But then you think about it a second and you're like, well, wait a minute, right? We started with a polytope, we did a projection, we get another polytope. Every polytope has a linear description. So this isn't helpful, right? So there's going to be some linear description. The question is more, can we get our hands on it, either as an analyst or computationally in an algorithm? So really what we want is a computationally useful description of the projected polytope. So one stronger definition would be, well, maybe you'd like a set of inequalities that you can separate over in polynomial time. After all, that's what we had in Bordas theorem. So it turns out we can get away with an even weaker assumption about what would be a useful Bordas-like theorem. All we assume is that, okay, so you need to come up with a bunch of linear inequalities describing the projected polytope, and it should be the case that, if I give you a point and I give you allegedly one of these inequalities, you should be able to recognize it as a valid inequality and check whether the point satisfies it or not in polynomial time. So put differently, what we really want here is a co-MP oracle for infeasibility in the polytope. Okay? But again, that's much weaker than assuming something like you can separate over the polytope in polynomial time. So that's our formal definition of a border-like theorem. And then what's the formal impossibility statement? The formal impossibility statement says unless sharp P, unless P to the NP is equal to sharp P, then there's no border-like theorem for pretty much, all of the, next steps you might want to push it. Okay, so we did this on a case-by-case basis, so it's not, it's a little bit ad hoc, but we said, what are all of the next simplest situations where you might want to prove Bordas theorem to? And on a case-by-case basis, we proved sharp P hardness results, which combined with sort of a general meta theorem implies that you cannot have these Bordas-like theorems. Okay, so we're really unaware of any candidate problems where you might be able to extend Bordas theorem to, that are economically interesting. Okay, so I'm going to have to, again, I'm happy to stay on after the talk ends if people want me to talk a little bit about the proofs. Let me at least flash this slide because I think there will be some people who find this interesting. So details are in the paper. It turns out that for one of the auction settings we consider, so-called public projects, there's actually a very tight connection between Meyerson's optimal auction theory for public projects and some, well-known results in Boolean function analysis. So, for example, the fact that, if you want to maximize any weighted sum of influences, it suffices to use a linear threshold function that has an analog in auction theory, which says that optimal auctions are always virtual welfare maximizers in some sense. So again, I apologize I can't talk about this in more depth, but the paper does have a discussion of this, I think, very neat connection. Okay, so wrapping up, so what was the theme? So the theme is that there were a number of problems in economics where the statement of the problem didn't seem to reference computation, and yet it turns out complexity is crucial for understanding these barriers. So we saw an example about non-existence of Horizon equilibria, an example about how you prove that equilibria cannot be near optimal when you have communication lower bounds, and then at least briefly I tried to give you a taste that certain economic theorems which are really about tractable polytope descriptions, again, suitable complexity theory allows you to rule out generalizations of those. As far as open questions, I think Grant had a question which was sort of about this, which I think is interesting. You could take some of our unconditional conditional results and make them unconditional. So maybe my favorite question of this type is with respect to the Bordas theorem case. So we proved conditional impossibility results, but of course we also have a lot of machinery now for proving unconditional lower bounds on polytope descriptions through extension complexity. So I think it'd be really cool to have some extension complexity lower bounds for these projected polytopes that arise in auction theory. And all of this work is very new, and so somehow at this point I'm just feeling like probably there's a lot more barriers of this form. So I think we should try to find them. So thanks for having me. I'll stop there and happy to stay on to take more questions.
Thanks, Tim. Questions? I have a question. Can you go
Sure.
to the last slide, the last but one? Yeah, so
Which
I
one?
know, actually, yeah, the Boolean functions thing. I'm just trying to understand the second statement, that it sharp be hard to determine whether a given vector of sharp parameters is feasible. Do we actually know it sharp be hard? Like, I mean, computing the sharp parameters is sharp be hard, but determining whether like given sharp parameters whether it's feasible or not.
Right. So this sort of follows from the equivalence of separation and optimization. So if you could solve the feasibility question, then you could solve certain optimization problems over the polytope of Chow parameters. And so those optimization problems you can then kind of prove directly or sharp be hard. We basically, we just looked at reduced from counting the number of knapsack solutions.
Okay.
Yeah. Yeah, but so from this connection, it's not clear you need this connection to prove these results on the Boolean function side, but in doing so, we learned some new things. For example, intractability of membership of the polytope of Chow parameters.
Okay. Do we have any more questions?
Hello. Yeah, I'm talking about the very first topic that was dealt today, the welfare and the utility.
Right.
And in the case of a fractional situation, the complexity of finding the one is the same as the complexity of finding the other, if and only if Walrasian equilibrium exists. Is that true?
Yeah. So this is the fact 2 here. The economic question would be, when do you have existence? The kind of more algorithmic sounding question would be, when is a certain linear programming relaxation exact? And it turns out instance by instance, those two questions have exactly the same answer. So you have existence exactly when the linear programming relaxation is exact.
Okay, so we have both. So unlike the other case, the converse here is also true.
Correct.
So, okay, thank you.
Yep.
If we don't have any more questions, then we can probably take this off the air.
Okay, so let's remind everyone, next week on India we have...
Yeah, next week we have Pietro and Deek, and 2 weeks from now we have Pietro and Deek, and
right.
4 weeks from now we have Virginia Williams. So thank you, everyone. We are taking this up air now.
Thanks everyone.